Welcome back. Today's topic is a continuation of the previous topic. In the last class, we have computed magnetic potentials due to different current configurations, and we have solved the problems on those things. So we'll continue on these magnetic potentials, and we'll try to compute for a few more cases. So I hope that by the end of this video lecture, you will be able to compute the magnetic potentials for different current configurations. Coming to the first problem, find the current density J due to A is equal to, this is the value, and he is mentioning that the medium is of free space. If the medium is of free space, it indicates that we know that mu is equal to mu naught into mu r, and mu r is equal to 1. This is an indication of the free space. So your mu is just only mu naught, which is nothing but 4 pi into 10 to the power of minus 7 without the units. And he's asking us to determine current density J with the potential which has been given for us. This is magnetic vector potential A. So how to determine J in terms of A? We do know that mu J is equal to del cross A, which we have gone through in the previous video lecture. So we will try to utilize this formula and determine the current density having this particular parameter. Now, one more thing which you should remember is that if you carefully see, this has been in a Z, isn't it? So which means that you do have three coordinate systems, x, y, z, r, phi, z, and the other one is r, theta, phi. Cartesian system, cylindrical and spherical system. If you see, it is already in Z, so this is ruled out option. And in these two, you do have a choice now. And one more thing, if you carefully see, R has been mentioned, which means that it must be likely a cylindrical system. So this is the way how we identify the system. Now, we need to solve this problem in cylindrical coordinate system. Okay, so this is mu J. We know that this is the formula, and now having already identified that this is in cylindrical coordinate systems, we need to perform this operation. We know that del vector, see, del vector is this vector. It is mu r, mu phi, and mu z, right? For mu r, it is dou by dou r. For mu z, it is dou by dou z. But for phi, since it is not a length, I will try to implement 1 by r. This is del operator. So now I will. So this is your given magnetic potential. So first of all, let me find out del cross A, and next I'll find out del cross B, which is equal to mu J, and then I will find out J. So first of all, B, which is nothing but my del cross A. So del cross A, this is del operator. So now this is a cross product, right? Del operator, I do have del operator. It is dou by dou r of mu r plus 1 by r dou by dou phi of mu phi plus dou by dou z of mu z. This is del operator, and this is A operator. You don't have any components here. You do have only one component, and it is 10 by r square mu z. So this is the way how we perform the operations. Cross product. So B is equal to, these are the components. So I am writing down these components here, dou by dou r, 1 by r dou by dou phi, and this is dou by dou z. And here I don't have, so I'll take the 0, 0 and 10 by r square. So you need to determine the det of this one. So if you do the determinant, so if I take this one, this is mu r bar, this is, so what I'll get, 1 by r dou by dou phi of 10 by r square minus, this is 0, right, minus u phi into, now if I take u phi, so this is 1, right, So this is dou by dou r of 10 by r square minus 0 plus uz. If you see, for uz it is this one, right? It is 0 minus 0. Now if you do this one, if you get, see, if I do it with respect to phi, I don't have any phi component here, so I'll get 0 here. So this will become 0. This is already 0. This is 0 and this is also 0. So I do have only this component. So if you see, I am differentiating with respect to r. So what I'll get, it is minus 2 by r cube, right? So already 10 is there and already minus is there. So I'll get 20 by r cube u. This is my b vector. Okay, I think this is plus, I think, right? So 20 by r cube u. So once I do have it, now, yeah, I think it is plus or minus. Let me check once again. Minus u5, and this is, yeah, I think it is plus. So now again I am supposed to do, because mu j is nothing but del cross b, again the same thing, but here b is in terms of 20 by r cube, so I'll get 20 by r cube. Again the same phenomenon here. For ur, I'll get 0 minus 0 plus u5, sorry, here minus u5, I'll get, yeah. So 1 minute, okay. I'll write it here. What is mu j? This is ur into, right? This is 0 minus dou by dou z of 20 by r cube minus u5, you will get 0 minus 0 plus uz, you will get dou by dou r of 20 by r cube minus 0. So this component is automatically 0 because it doesn't have any z component. Here you do have an r component. So what you will get ultimately minus 60 by r power 4 uz. Okay. So this is your mu j. I think here you will get minus. So this is mu j. In terms of z component only, you do get the values. And in free space, we have already seen this. Mu is equal to mu r will be 1. And this is mu value. So if I want j, what I will do, minus 60 by r power 4 uz by that 4.2 10 to the power of minus 7. If I do this, this is my final value. Okay, so this is the way how we determine the current density when A is given for us. Now we will move on to the problem number 2. If you carefully see, determine the magnetic flux density at the point if the vector magnetic potential is given by, so this is A and they want magnetic flux density. This is a simple problem. This is B is equal to del cross A, isn't it? A is already known, del operator, whether we should choose Cartesian or cylindrical or spherical. If you can carefully see, this is in x terms, so we can directly choose Cartesian system. So let's try this one. So B is equal to del cross A, del operator, we know this del operator in x, y, z. So this is A already, which has been given for us. It is having only x component here, y component and 0 component. Y component is 0 and z component is also 0. So B is equal to del cross A. So we have already tried this one. This is ux, uy, uz. This is del component and this is A component. So if you do this one, what you will get, this is ux into, right, 0 minus 0 minus uy into, this is 0 minus dou by dou z of 10 by x square plus y square plus z square plus uz into, again you will get 0 minus dou by dou y of 10 by x square plus y square plus z square, right? Right. So now if you solve this one, yeah, this is the expression. Now here you have 0. Here if you do this one, this is 1 by x square plus y square plus z square whole square into internal differentiation with respect to z is 2z, right? Here also you will get 2y as internal differentiation because you are doing it with respect to y. So if you take these things common, this is 20 by x square plus y square plus z square. This is zuy minus y uz. Now you have been given that xyz is equal to 3, 4, 5. So if I substitute the values here, so this is my final answer. Okay. So I hope that you have now understood how to obtain different quantities when magnetic potentials have been given for us. Okay. So try to solve this problem at home and come back tomorrow. We'll discuss more problems in the class. Thank you.